If you have any dealings with the sea, and especially if you live in these islands, you can hardly fail to notice that water rises and falls twice a day with the tide. And if you take a camera, if you're something of a trick photographer at any rate, you can catch it in action. The next thing you're bound to notice is that the tide changes every day. Every day, high water is on an average 50 minutes later. And then, if you have a boat, you'll certainly find out that the tide doesn't rise everywhere at the same time. It moves along the coast. And then, if you're at all curious, you'll probably discover that even around the coast of the British Isles, tides can come in all shapes and sizes. At Lowestoft, the average tidal range, that's the distance between high water and low water, is 5 feet. At Sheerness, it's 14 feet. And at Bristol, it's very large indeed. It's 40 feet. But further afield, in the Baltic and in the whole of the Mediterranean, the tidal range is no more than 2 feet. The strip of beach that makes the fortunes of the tourist trade is never covered by the water. It even has to be raked clear by the umbrella owners. But conversely, it's in the Bay of Fundy that the world's largest tides are, and there the tidal drop can be 50 feet. The wide stretches of the bay empty like a bath, and the incoming water seems to swallow a landscape. In fact, one of the local fishing techniques is simply to stretch a net in the water and drive out later on virtually dry land to collect the fish. The Bay of Fundy is here, between Nova Scotia and New Brunswick in Canada. And that's not the end of it. Over most of the British Isles, there are 2 tides a day, 2 high waters and 2 low waters. Southampton even gets 2 double high waters, but we'll talk about that later. In the Gulf of Mexico, and amongst other places, there's only 1 of each. In Vancouver and on most of the Pacific coast of North America, there are mixed tides, 2 highs and 2 lows a day, but of very different heights. And just to round it off, there are everywhere regular sequences of neap tides and spring tides. Neap tides have unusually low high water and unusually high low water, and spring tides have unusually high highs and unusually low lows. We filmed a recent spring tide going out at Rye in Kent. The camera was set up at 8 o'clock in the morning, and filming went on until the middle of the afternoon. It's quite a spectacular drop over the course of the day. I've been reeling all this off just to convince you that the behavior of the tides isn't as simple and straightforward as they might be. If you only want to know roughly what the tide will be doing so you can plan your swimming or dig lugworms up, then a general idea of the factors controlling the tides will keep you happy. But if you happen to be driving, say, a large sailing ship with a deep keel, or even running a shipping line with ships of all sizes and shapes, using all kinds of ports over the world, then tides matter a great deal. Missing a tide will cost you money, and if you end up with, say, the Queen Elizabeth aground, that will cost you very much more money. So how much do we know about tides? Here from the Tidal Institute and Observatory, which is part of the University of Liverpool, is its director, Dr. Rossiter.
We do have some explanations for the bewildering variety of tides all over the world. We know how they're generated. Knowledge, in fact, built on very ancient observations. The Greek navigator Pytheas is credited with doing the first serious work on tides somewhere around 350 BC, and he is also supposed to have related tides to phases of the moon. But it was Isaac Newton who gave us the physical and mathematical understanding that enables us to base our modern tidal predictions on the gravitational pull of the sun and moon. They act on everything, on the atmosphere around the Earth, on the Earth itself. It moves about 30 centimeters under its own tide. And tides have even been detected in lakes and wells, and possibly even in our own bodies. But in water, it takes the vast depth and expanse of the Atlantic or Pacific to build up tides of more than a foot or two. To understand the tides, one has to bear in mind the relative movements of the bodies in the solar system. The moon moves round its orbit around the Earth, and the Earth, of course, moves round the sun, as is shown in this rather simplified orrery, kindly loaned to us by the National Maritime Museum.
Imagine the entire Earth to be covered by a deep ocean. 250,000 miles away is the moon. Because the ocean on the right-hand side is nearer to the moon than the Earth is, the moon's pull on the water is greater than on the Earth, and a bulge is formed in the ocean on the right. But this isn't the whole story. What is not quite so easy to appreciate is that because the moon is nearer to the Earth than to the ocean on the left, it's as if the Earth is pulled away from the water, therefore causing another bulge. The water from these bulges has to come from the top and bottom. If we now imagine we're looking onto the North Pole, the Earth's rotation will be anti-clockwise, and any point on the Earth's surface will come under each of the high waters on the left and right, and each of the low waters at the top and bottom once a day. In this way, we have a semi-diurnal tide. But the moon is also moving round the Earth, taking the axis of the tidal bulges with it. This means that the lunar tidal cycle will be more than 12 solar hours. To be more exact, it will be 12 hours, 25 minutes, half a lunar day.
If we replace the moon by the sun in this explanation, we should again have a semi-diurnal tide, but with two important differences. In the first place, the solar tide cycle will be exactly 12 solar hours, because one rotation of the Earth is by definition a solar day. And secondly, since the sun is more than 400 times further away from the Earth than the moon is, its tidal pull is less than the moon's. On an average, 1 foot of lunar tide is accompanied by only half a foot of solar tide.
Now let's go a stage further and combine the two tidal bulges and see what happens during the lunar month of 29 days. At new moon, the Earth, moon and sun are in line, and the two bulges augment each other to give spring tides, that is high waters and low waters. At first quarter, about 7.5 days later, the moon's bulge is at right angles to the sun's, that is to say, they oppose each other. The combined bulge will be in the direction of the moon, but will be less pronounced than at new moon. We now have neap tides, that is lower high waters and higher low waters. If you watch, you will see the bulges grow larger as we come up towards full moon. At full moon, the bulges are in line again because the sun and moon are in line again, and so once more we have spring tides. And at the last quarter, we are back to neaps. Of course, in this diagram, the scales of distance are distorted. If we record a month's tides and then condense the scale, we find that it shows very clearly the alternate high and lows of the spring and neap cycle. But to understand how diurnal, or one-a-day tides arise, we must look at our Earth-Moon system from the side, that is, in the plane of the equator. The moon's orbit around the Earth isn't always in this plane. Sometimes the moon is below the equator, sometimes above. This declinational effect causes the axis of the tidal bulges to move below and above the equator. So a point on the rotating Earth comes under high waters of different heights in the course of a day. And the low waters will also be different heights. Now, if high waters are alternately high and low, this is the same thing as a diurnal variation of the tide.
Well, even that is a highly simplified account of the situation, and it meant considering the Earth as if it were entirely covered by the ocean. But the Earth isn't entirely covered by the oceans. There are land masses which interrupt and deflect the tidal flow. They do this in several ways.
Every body of water, according to its length and depth, has its own natural period. The tank we have in the studio has water in it to a certain depth, and the natural period of this body of water is about 1 1/3 seconds. If I move this tank very quickly and try to get an oscillation of the water in the tank, I can't do it when I use that period of movement. However, if I tilt this at a period of approximately 1 1/3 seconds, you will see that the water begins to move much more, and if I were to continue like this, it would of course slosh over the end of the tank. Most children can do this without any training at all. And now let's imagine that instead of the force of my hand applied to this basin, a gravitational force, a pull from the sun and moon with a period of half a day, is being continuously applied to various oceans, seas, and gulfs. It's those with a natural period nearest to half a day which will respond most readily. And these are the areas where the largest semidiurnal tides will be found. The Bay of Fundy, which has the world's largest tides, is calculated to have a natural period very close to 12 hours. So it responds intensely to the 12-hour period of the tide. But the Gulf of Mexico has a natural period of 24 hours. So it only responds to the 24-hour or diurnal tide. The semidiurnal tide from the ocean hardly affects it. The natural periods of the Baltic and Mediterranean have no counterpart in the range of tidal periods, so they cannot respond to the direct pulls of the sun and moon. And because their entrances are too narrow for the ocean tides to get in, they are both practically tideless. Another very important way in which the ocean tides are modified is when they cross the continental shelf, marked white on the globe, and pass into the coastal shallows. As a general rule, the shallower the water, the stronger the currents. The seabed then acts as a brake on the water, and this bottom friction takes energy out of the tidal flow. The greater the current, the more energy is lost. You can see how it works in a laboratory model. The profile of the tidal wave is distorted in much the same way as a surface wave steepens when it approaches a shelving beach. This is a speeded up version of what the tide does in the Thames estuary, which is an extreme example of shallowing. You can see how the tide wave steepens as it reaches the really shallow section. We can think of a tide as a kind of wave, but one with a very small amplitude compared with its wavelength, which can be at least 500 miles between crests. These distorted or shallow water tides are very noticeable in British waters, though they don't always take this form of a steepening of the wave front. In the Thames, the Severn, the Mersey and the Clyde, they do. But at Southampton, the relationship between tidal height and tidal current is such that the shallow water effect produces the well-known double high water. It's often said that this Southampton effect can be very simply explained as a result of the main tide coming around both sides of the Isle of Wight. But in fact, the true explanation is far more complex than this and involves the effect of friction in these shallow waters. An extreme case of tidal distortion sometimes happens just after low water and is known as a tidal bore.
In Britain, there are tidal bores in the Severn, Trent and Dee, and they're quite an attraction for tourists. But bores depend very much on the shape of the riverbed, so if the riverbed changes, the bore may not arrive. Just looking at bores makes engineers think about the power locked up in the tides. Designing a practical power station really means finding a way of extracting continuous power from a source that reaches its peak only twice a day. To produce the first tidal power station has meant years of careful study with scaled-down hydraulic models of the proposed plant. The French designers of the new power station at Reims have chosen a site with a tidal range of 40 feet, and the power plant itself is a system of turbines with reversing blades allied with alternating current generators. This power station is expected to provide enough electricity for an industrial city of 250,000 people, something like 540 million kilowatts a year. The tides in the global ocean contain power of the order of 1,000 million kilowatts a day. Most of it comes from the energy contained in the Earth-Moon system of rotation, and most of it is dissipated in shallow seas. Tides are so complex that probably the only way to get a clear idea of what's happening is to look at an animated chart of the average tide moving around the British Isles. The dark shading shows the highest water levels, the light shading the lowest. Here, the whole tidal cycle of 12.5 hours has been condensed into 15 seconds. As the tides sweep in from the Atlantic, you can see that the largest tidal ranges round the British Isles are in fact on the French coast. This, of course, is the location of the new Reims power station. These large tides are due to the effect of the Earth's rotation, which deflects moving bodies to the right in the northern hemisphere. So the tide, moving from the west, is deflected to the south. Apart from this complication, the response of the English Channel to the Atlantic tides is a simple seesaw motion, with low water at one end when it's high water at the other. Though perhaps you may detect a slight hesitation of the tide in mid-channel when a large area has high water at the same time. In the St. George's Channel and the Irish Sea, it's interesting to see that the response of the oceanic tide is very similar to that of the English Channel. In fact, the two channels are roughly similar in shape and depth. Here again, the range of tide is greatest on the right of the channel, and as the tide moves north, there is the same tendency to hesitate. The whole of the Irish Sea has its high water within a few minutes. But in the North Sea, which is a much broader stretch of water, the picture is quite different. The range of tide is smaller, and the effects of the Earth's rotation take another form. As the high water comes round the north of Scotland, it is deflected to the right and hugs the British coasts. At the southern end of the North Sea, the tide is partially reflected. It goes north, and the Earth's rotation again drives it right, onto the continental coast, on its way back to the Atlantic. In other words, this is a rotary system, in which the tide travels round points of no movement, which are called amphidromic points. There are two of them in the northern North Sea, and there is another one in the southern North Sea, and still another off the north of Ireland.
Well, all that explains how tides work, why there is such a diversity of tidal effects. But very few people really expect to carry all that information around with them. Most of us content ourselves with a summary of the tides for the year, with tide tables like this, published by the Hydrographer of the Navy. You can buy them in most boat shops. But how accurate are they? Can tides be predicted with the precision required by, say, the navigators of a giant modern oil tanker drawing 60 feet, crossing a bank in the middle of the English Channel?
All these tidal predictions we use are based on past events, the past tides. They are worked out according to a scheme developed in the 19th century by Lord Kelvin. It's called the harmonic method and covers both analysis and prediction. Kelvin even invented a special calculating machine to do the computations. Nowadays, all this work has been programmed for electronic computers, and 1 year's tidal predictions for a given port can be prepared in as little as 2 minutes. They are based on the past observations for the port, its geography, and of course the relative positions of the Sun, Moon, and Earth. But unfortunately, these predictions are only accurate on average, since the weather, an unknown quantity, has to be included. Weather can make tides predictions disastrously wrong, as they were on the night of the 31st of January 1953. That night, storm-force northerly winds swept enormous volumes of water onto the low-lying, vulnerable coastlines of Holland and southeast England. This was a storm surge, which is often popularly and incorrectly called a tidal wave. That night, in Holland alone, 1,800 people lost their lives, and 300 in Britain. What caused it was the deep depression up here. The storm winds of the depression swept round in this direction, dragging the water with them. The surge of water from the storm traveled down the North Sea. To this was added a general rise of the level of the North Sea due to the extremely low pressure at the time. This joined with a normal high tide to overrun the low-lying coast of Holland and East Anglia. Unhappily, the predicted tide was a high spring tide. The actual sea level was 8 feet higher than the predicted tide and lasted many hours. From this, it is possible to calculate the storm surge. The combination of all these unfavorable circumstances has been calculated to be likely only once in 400 years. So we may have to wait for 800 years before it happens again. On the other hand, it may happen the next spring tide. But this isn't just a tidal problem. We need to know much more about the influence of the weather on the seas, and that in itself is an enormous and difficult area of research. Probably we won't get solutions for many years. But as far as weather conditions can be known in advance, we're trying to incorporate them into the computer forecasting of tides. If we take the waters around the British Isles, which include the Norwegian Sea, the North Sea, the Irish Sea, and the English Channel, and divide them into small squares like this, we can feed a computer with information about each of these squares: the depth, the coastlines, the tides along the continental shelf, and the weather. The computer can be programmed to use all this material to predict the behavior of the water at each point. In fact, we can build a mathematical model of the estuaries and seas. The experimental results of this testing calculations against past events, or hindcasting, have in fact been remarkably good. On a larger scale, attempts are being made to make numerical calculations for the tides of the world's oceans. The idea is to start off by treating them as simple shapes, considering theoretical oceans of constant depth, bounded by lines of latitude and longitude. But to check the results, we need new instruments, especially instruments to measure the tides, not at the coast where we usually measure them, but out in the deep ocean.
Well, on this point, there's perhaps some good news. This summer, at least one new tide recorder for the deep sea has been undergoing tests. At the Scripps Institution of Oceanography in California, they've been testing a strange-looking object at sea. It's called a tide capsule. It comes in 2 parts. One of them holds batteries and a set of transducers, which are so sensitive that if the sea level above them changes by as little as a millimeter, the pressure change at the bottom is recorded. They also record water velocity and temperature. The upper buoyant part of the capsule, separated from the transducer part by 50 feet of cable, is also subdivided into 2 bubbles. The bottom one consists of recording instruments which put onto tape the measurements taken by the transducers. The top bubble is a transmitter-receiver. This transmits information about the instruments back to the ship and also sends an alert signal if anything goes wrong. The last part of the assembly is a receiving hydrophone, which allows the capsule to receive commands from the ship. Once submerged, the whole capsule starts its descent to the bottom 6,000 feet below. The ship sails away to await its signals. The capsule doesn't wait till it gets to the bottom before it starts work. All the way down, it transmits guidance information about its depth and the state of its instrument pack, which is all recorded in the capsule's own mobile laboratory on board the ship. The information about the experiment isn't transmitted. It's being stored on tape inside the capsule itself. To retrieve the capsule, a transmitting hydrophone is put in the water and a coded signal is sent out. On the signal, the capsule fires an explosive bolt to release itself from its heavy anchoring batteries and return to the surface. Once there, it transmits a homing signal which enables the ship to find and retrieve it. If any fault develops in the instrument, the capsule automatically releases itself and rises to the surface, where it starts to transmit its alert code. Once on board, the retrieved capsule cannot be safely opened until it's inside its air-conditioned laboratory, where the tapes recording the deep ocean tides can then be removed. Let's hope that this kind of instrument will contribute to better and more accurate tide predictions in the long-term future. Clearly, we've not yet finished our business with the tides and with the enormous and complicated movements of water which are involved. In fact, scientists in this field dream that one day a method will be found for predicting tides not from past records but from first principles. It's become a kind of holy grail. All over the world, hydrodynamicists are being drawn by this quest into strange territories of uncharted mathematics. But so far, the prize eludes them.